In Chapter 6, Lesson 1B, we're going to talk about the concept of a slope field, and the slope field being a visual representation of different solutions to differential equations. So it helps us visualize sort of how the path of a solution might go according to its slope tendency, positive slope, negative slope, and concavity. What a slope field will give us is it's using the differential equation, which gives us the slope at any point. We draw a small piece of the slope at that point, and when we repeat that process over and over, we get what's called a slope field. So let's work on creating a slope field together. All right, given the differential equation modeled by cosine of x. So the slope at any point along the y-axis, so at any point where x is 0 and for any y, well, when we put 0 in to the cosine function, okay, we put 0 in for x, we're always going to get 1. So that means along my slope field, I draw a little piece of a line, of a tangent line, a linearization, that has the slope value of 1. So when it crosses the y-axis, it will be doing so with a slope of 1. All right, now let's take a look at any point with a x-coordinate of pi. Okay, any random y-coordinate, but an x-coordinate of pi. All right, well, if I put pi into cosine of x, I'm going to get -1. So if this is pi on my x-axis, then along these values, I'm going to do my best to draw little pieces of linearizations. Oh, I didn't like that one. That all have a slope of -1 along that sort of vertical column. At negative pi, if we plug negative pi into our differential equation, I will also get -1. So any y-coordinate there will have a linearization, or a little piece where we have a slope of -1. How about pi halves? Well, if we plug pi halves into cosine, we're always going to get the value, okay, of 0. So if I take pi halves here and I plug it into cosine, I'm always going to get 0. Regardless of what the y value is, the x value of pi halves will give me a piece of 0. So then I know that at pi halves, I have all of these little linearization pieces that will have a horizontal tangent. In fact, so will negative pi halves, and so will the other odd multiples of pi halves. They will also all have a small piece of a linearization with a slope of 0. All right, what about at 2 pi? All right, so let's see. We should be filling in our blanks as we go. The slope at any point 0y, we determined that that would be 1. The slope at any point pi or negative pi would be -1. Slope at all odd multiples we determined would be 0. So along 2 pi, again, if we plug in plus or minus 2 pi, we are again going to get a slope of 1 along all of those lines. So I'll be back to a slope value of 1. Okay, so then what we have here is a visual representation of what's called a slope field. And so any line moving from left to right would have to follow in between the slope field, maybe necessarily without crossing something. So let's say we entered the slope field with a slope of 1 here. When I get to a negative 3 pi over 2, I now need to bend in such a way that I've got a slope of 0. And I continue moving right, and as I cross the plane of negative pi, I now have to have a negative 1 slope. And then when I get to negative pi halves, I now have to have a slope of 0 again. And then I'm changing to a positive slope, and then 0, changing back to a negative slope, and then 0, and then back to a positive slope. I didn't finish this part. And so this creates what we recognize as the graph of sine, crossing the y-axis at some constant, but the graph of sine. So this represents the antiderivative of cosine, which is a sine graph, plus some constant where it's going to cross the y-axis. And so a slope field is a visual representation, and what we get out of that is the visual of a sine graph. Okay, let's try constructing a little bit different differential equation based on both the x and the y coordinates. So let's start right at the origin. At the origin here is 0, 0. So if I plug 0 and 0 both in, I'm going to get the value 0, which means I have a horizontal linear piece I need to put in right there. As I move across the x-axis, the y value is going to stay 0, but the x value will continue. So at 1, 0, I have the slope of 1. As I move to 2, 0, I'll have the slope of 2, so slightly steeper. Now because it got steeper as I move to the right, this means it is concave up. Positive, and then getting more steep as it goes. At negative 1, 0, I'll have a negative 1 slope. And at negative 2, 0, okay, again, showing positive concavity. Let's try the point on the y-axis, 0, 1. That will have a slope value of 1. So I'll construct a linear piece with a slope value of 1. And so notice that these two both have a slope value of 1, so that they should be slanted relatively the same way. Are there any other places where I might have a slope value of 1? Well, I can also get a slope value of 1 by having negative 1 for x and 2 for y. So I go to the position, negative 1 for x, 2 for y, and I'll have a slope value of 1. And that's kind of in the diagonal, so I start to think, well, maybe everything along that diagonal is going to have a slope of 1. What about 2 and negative 1? I go to that position. Okay, so all of these along this diagonal line are all sharing the same slope. Will that be true for other dots that are following kind of on a diagonal line? So what if we checked all of these values? Right, well, that would be checking values like negative 2, 2, negative 1, 1, 1, negative 1, 2, negative 2. And sure enough, all of those points are going to have the same slope as they did at the origin, which is a slope of 0. Let's keep it consistent. So anything that crosses through that line y equals negative x is going to have a slope of 0. These are all going to be a slope of 1. These are all going to be a slope of 2. This is going to be a slope of 3. And then a slope, excuse me, -2, -3, -4. I'm trying to get steeper as I go. This line here where I've got all of a slope of 1. A slope of 1 is the only place where there's no concavity. It's not concave up, it's not concave down, it's concave neutral. All right, let's keep creating our slope lines. This will be 1 plus 1, so a +2. This is a +2, +3. It's hard for me to distinguish now, but they're getting steeper and steeper and steeper as we move along those lines. So this whole upper section, I'll try and maybe highlight it. This whole upper section, which we consider to be above the diagonal line, is all going to have increasing slope, increasing at an increasing rate. So that would be considered positive concavity. Whoops, different marker, there we go. Okay, there's positive concavity. And then the section below, this line down here, below the diagonal y equals -x, that section has negative concavity. If we try and draw a line through, it's going to be going like that. So you can kind of see how it has negative concavity. Whereas if we draw a line maybe having horizontal and then having to increase in slope, that one has positive concavity. Okay, a note about slope fields and where they're valid and where they are not valid. Okay. A slope field is only valid within, if you have asymptotes. An asymptote sort of divides a graph into different regions. Your slope field is only valid in the region that contains the initial condition. So if you've got an asymptote where you've got vertical slope and your initial condition is on that side, the left side of the asymptote, well then your graph is only going to be valid on the left side of the asymptote. Okay, so it has to be in a continuous section containing the initial condition if you have an undefined part of your undefined slope in your slope field. So here we're given the initial condition -2 and 1/4. Well, let's construct our slope field first. We run into a problem right away because x can't be 0. If we try to use x as 0, we're going to have an undefined slope. So that means I have a vertical asymptote going right down the y-axis. When x is 1, all of the slopes are -2. So let me draw linear pieces of -2. When x is 2, all of the slopes will be -2/8 or -1/4, which is it's still negative, but not quite as steep as before. So we see a concavity change. As it's getting less steep, that becomes concave up. On the left side of the asymptote, when I have negative values, when x is -1, all of the slope value increments will be +2. And then when x is -2, all of the slope values will be 2/8 or +1/4. All right, now our initial condition puts us at -2 and then 1/4. So that's about, let's estimate, about right here. So starting from there, we want to follow the slope field pattern of that, but we can't cross the vertical asymptote. So it's going to be coming up with an increasing slope, getting to the point maybe where it's vertical. So coming up maybe through there. So just watch out for vertical asymptotes and if you're asked to construct or asked to validate a slope field, that you'll stay within the side of the vertical asymptote where your initial condition is. Okay, on your calculator, you can also generate slope fields. In Y1, you would put the differential equation itself. So if I was constructing a slope field for this problem, I would put -2 over x cubed in my Y1. Okay, the derivative itself goes in Y1. That's all you need. And then you run the slope field program, and it will generate bits of little linear pieces, much like what I constructed by hand, but it will do more of them at different incremental values for you to see. So you can always confirm what you've done by hand by maybe taking a look at your graphing calculator. I can't guarantee whether a slope field question will show up on the calculator or non-calculator section of the AP exam, so we just have to be ready to do it either way. I hope you've had a good start to your week so far, and I look forward to being together with most of you on Tuesday. Some of you will be gone, but we'll all be back together on Thursday. All right, so hope you're having a good day. See you later.